And now we study the logarithmic function, or the logarithm function. So first recall that the exponential function f of x equals b to the x is 1 to 1. This means that there is a unique inverse function such that f inverse of b to the x is x. We call this inverse the logarithm base b. So a logarithm base b of a positive number x satisfies the following condition: for x greater than for x greater than 0, b greater than 0, b not equal to 1, y is equal to log b of x, log base b of x, if and only if b to the y is equal to x. That is, y is the power to which b must be raised to get x. And this is, of course, read log base b of x, or the logarithm of base b of x. So what we're going to do is we are going to write the logarithm equation in exponential form. All right, so for this one, log base 6 of the square root of 6 is equal to a half. If and only if, so this double arrow means if and only if 6 to the 1/2 power is equal to the square root of 6. So this is known as the exponential form. All right, so now log base 3 of 9 is equal to 2. So we say log base 3 of 9 equals 2 if and only if 3 to the second is equal to 9. So again, that is our exponential form. Now we're going to write the exponentials in logarithmic form. So 2 is equal to 8 if and only if log base 2 of 8 is equal to 3. So this is our logarithmic form. 5 squared equals 25 if and only if log base 5 of 25 is equal to 2. And 10 to the minus 4 equal to 1 over 10,000 if and only if log base 10 of 1 over 10,000 is equal to negative 4. All right, so we're going to go ahead and evaluate some logarithms now. So we want to evaluate log base 4 of 64. Well, let's write 64 as a power of 4. Well, 64 is 4 to the 4th power. 4 to the 3rd power. Right, because 4 times 4 is 16. Now 16 times 4, right, 24, carry the 2, 4, 6, right, 64. So this is just 3. So log base 3 of 1 over 27 is equal. So again, we want to try and write 1 over 27 is a power of 3. So it's 1 over 27 is 3 cubed. And using laws of exponents, that is 1/3 all cubed. And so I'm sorry, I shouldn't have done that. We want to use a different laws of exponents and write this as 3 to the minus 3. There we go. Now the log is negative 3. Now, There are two bases that are used more than any other base, and those bases are 10 and e. Now, we already saw that e is called the natural base. We call 10 the common base. And because of how common these two bases are, we have given the special notation. Log base 10 is simply written as log of x. Log base e of x is simply written as ln of x. And this is called the natural logarithm. So log of 10,000. Now remember, this is understood to be log base 10. So we want to write 10,000 as a power of, or as base 10, right? It's a power of 10. So 10 to the fourth. So this is equal to 4. So log of 123. So this is, again, base 10. However, 123 is not a power of 10. So we will have to use a calculator to evaluate this. And I will show you how to evaluate a log base 10 on a calculator in a tutorial video, which should be the next video in this list. But for now, I'll just show you what it is. It's 2.0899. So ln of 500. Now, since ln is log base e, we want to write 500 as a power of e. Well, it's not a power of e. So again, we'd have to use a calculator. And again, I will show you in a tutorial video, which should be the next video in this list, how to do a natural log on your calculator. But this will wind up being 6.2146. Now we're going to study some properties of the logarithm function. Now, since log base b of x is the inverse of b to the x, we would have the domain being the range of b to the x, so 0 to infinity, and then the range would be the domain of b to the x, which is minus infinity to infinity. So let's identify the domain. So domain of log base 2, whatever you're taking the log of has to be larger than 0. So this means x would have to be larger than -3, and so our domain, -3 to infinity. And whatever we're taking the log of, it does not matter the base, it has to be larger than 0. So 5 would be larger than 2x, which means that 5 halves is larger than x. Another way of writing this is x is less than 5 halves. So the domain is -infinity to 5 halves. All right, so some more properties. Consider the logarithmic function of the form log base b of x, where b is positive and b is not equal to 1. Then f of x would have the following characteristics. It's a one-to-one function. It has a vertical asymptote at x equals 0. Right? We already looked at domain and range. Domain is the set of all positive real numbers. Range is the set of all real numbers. It's going to have an x-intercept at 1, 0. It will not have a y-intercept. It's an increasing function if b is larger than 1. And it is a decreasing function if b is less than 1. So here's comparison of two graphs. One where b is greater than 1. One where b is less than 1. Right, we can see that in the case of b larger than 1, it is strictly increasing. In the case of b less than 1, it is strictly decreasing. So to graph a logarithmic function, first, Draw and label the vertical asymptote x equals 0. As in the previous lesson, I typically will not label the vertical asymptote. I will represent it with dashed lines. Plot the x-intercept. Plot the key point B1. Then draw a smooth curve through the points. And state the domain and range. And again, I typically will not state domain and range. So let's sketch f of log base 5 of x. Right, so there's our coordinate system. Now it's base 5, which means it's going to be increasing. Right? We have our asymptote right here as the y-axis. It crosses the x at 1, 0. I'm sorry, 0. Yeah, 1, 0. Right, so I'll put a point there. And then 5, 1 is another point. So our graph would look something like this. Something like that. Now we're going to study the transformations. So for any constant c, the function f of x equals log base b of x plus c will shift the parent function log base b of x left c units if c is greater than 0. It'll shift it to the right c units if c is less than 0. It'll have a vertical asymptote now at x equals negative c. It'll have an x-intercept at 1 minus c, 0. Its domain will be negative c infinity, and its range will remain the same. Now for any constant d, the function f of x equals log base b of x plus d will shift the parent function log base b of x up d units if d is greater than 0. It will shift it down d units if d is less than 0. It'll have a vertical asymptote still at x equals 0. It has the x-intercept at 1, 0. It has domain of all positive real numbers, and it has range of all real numbers. Now for any non-unitary constant a greater than 0, the function f of x equals a times log base b of x will stretch the parent function log base b of x vertically by a factor of a if a is larger than 1. It'll compress the parent function vertically by a factor of a if a is less than 1. The vertical asymptote is still x equals 0. The x-intercept is still 1, 0. The domain is still all positive real numbers. And the range is still all real numbers. For any non-unitary constant a greater than 0, the function f of x equals log base b of ax will stretch the parent function log base b of x horizontally by a factor of 1 over a if a is less than 1. It'll compress the parent function horizontally by a factor of 1 over a if a is greater than 1. it will have a vertical asymptote at x equals 0. It'll have an x-intercept at 1 over a, 0. Its domain will still be all positive real numbers, and its range will still be all real numbers. Now the function f of x equals negative log base b of x will reflect the parent function log base b of x about the x-axis. The vertical asymptote will still be x equals 0. The x-intercept will still be 1, 0. Domain will still be all positive real numbers, and the range will still be all real numbers. The function f of x equals log base b of negative x will reflect the parent function log base b of x about the y-axis. Its vertical asymptote is still x equals 0. Its x-intercept is now negative 1, 0. Its domain is now the set of all negative real numbers, and its range is still the set of all real numbers. So that concludes our introduction into the logarithmic function. As I said, the next video after this in the list should be a tutorial showing you how to evaluate logarithms in your calculator, at least for base 10 and base E. Then after the next video, we'll be looking at some properties of logs.